Good afternoon. Today I am going to talk about myocardial T1 mapping, including clinical applications, T1 physics, and the practical considerations. In clinical applications, we have iron overload, fibrosis disease, which have low T1 values. And we also have diffuse fibrosis, acute infarction, which have high T1 values. The T1 values are actually affected by molecular tumbling. The molecular tumbling is just like eye pulse, so it causes T1 shortening. We have a BPP theory about T1 for solid and the liquid. The T1 constant is longer. For viscous liquid, the T1 constant is shorter. Around the protein, we have bound water and free water. The bound water is just like viscous liquid, so it has shorter T1. So in the myocardium, we have fat, bound water, and the extracellular fluid. So their T1 constant are different. So in different clinical applications, we have fibrosis with fluid accumulation. So it has long T1. For tissue iron overload and the fibrosis disease, they have shorter T1. In the diffuse myocardial fibrosis, because of the fluid accumulation in the extracellular space, so we have longer T1 here. To obtain T1 relaxation time, generally we sampled and fit the T1 curve to obtain the T1 constant. Usually we applied inversion recovery pulse, which is a 180-degree pulse, and then track the magnetization, and then obtain the T1 constant. In the clinical flare image is an example of inversion recovery. We acquire the flare image at the null point of the CSF. That's why we get zero signal in the brain ventricles. So we can use IR spin echo to acquire flare image. And then right now we have IR turbo spin echo, which is faster. But still, we still need long TR to allow MZ go back to the thermal equilibrium state. So imagining that you need 5 times of flare to get the T1 constant, because you need multiple points of TI values, and you need long TR for the T1 recovery. So it's not applicable for the breathol, right? So one solution is the look locker acquisition method, or the MOLLI in the myocardial T1 mapping. So what is look locker method? Remember flash, fast, low angle shot. We use eye pulse with very small flip angle, and eye minimally affects MZ So we use very small flip angle, and the magnetization is almost the same before and after RF pulse. So when we combine IR and flash, then we can track the whole inversion recovery curve. So that's the look-locker acquisition. We repeat the inversion recovery pulse for every K line and track the inversion recovery. The scan time can be reduced from 5 flare to just 1 flare. Okay, so this method was proposed by Look and Locker in 1970. Actually, I have a short story about the Look-Locker method. Dr. Look had a talk about this. He said, Don and I ended up in different laboratories, both of us leaving MRI behind. However, unknown to either of us, the seed we had planted in 1970 had begun to germinate in the 1990s. Our technique was soon given its own name, Look-Locker. I first learned of this in 2014 when ResearchGate sent an email stating that our paper had been cited many times. Of course, I was quite shocked and thrilled. It is interesting, right? Dr. Look didn't even know their method had its own name, the Look-Locker. So remember, for the Look-Locker method, I minimally affects MZ, but it does affect. So we actually need an extra correction for it. That's the blue equation here. And then we can use segmented acquisition to shorten the whole acquisition time from 5 to 1 to 1/3 of a flare acquisition. Or we can push it to the limit. We can use matrix size 256 by 128 and the ultra fast gradient echo, multi-coil, partial Fourier. The scan time can be reduced to 150 milliseconds. So single shot image becomes applicable during cardiac quiescent phase. So we can use one breath-hold with the balanced SSP readout to collect the whole inversion recovery curve. But wait a minute, how about the cardiac motion? Actually, we need ECG gating for that. So we can use ECG triggering and take a deep breath for one breath hold and to acquire 8 IR images. It seems perfect now because we can use 8 images to track the T1 recovery. But just wait one more minute. See, for the last 5 images, they have almost the same signal intensities. So they are actually less useful for T1 fitting. So we need some more modifications for that. We can use 2 Look-Locker within one breath hold. For the first Look-Locker, we use TI1. For the second Look-Locker, we use TI2. And in between, we wait 3 heartbeats for T1 recovery. The naming convention for this is MOLLI 333. And then we rearrange the 6 images. So it is just like we use 6 images to track the T1 recovery curve. And we assume that for the second 180-degree pulse, we assume full T1 recovery for it. Is it enough? Is it enough that we use only 3 heartbeats for T1 recovery? Actually, it will cause some problem because heart rate is different for different patients. So sometimes we use 3 seconds for the T1 recovery. Then this method can reduce heart rate variability. So we change from MOLLI 3 to MOLLI 3 seconds 3. Here comes the original MOLLI. We use a single bottle for that, and we acquire 11 images to track the T1 recovery. And then we rearrange the 11 images to calculate the T1 constant. The naming convention is MOLLI 335 or MOLLI 11. These are the actual images for MOLLI 11. The curve looks different, but remember that in MRI images, we generally only have the absolute values. So for different tissues, we have different T1 recovery, and then we can calculate different T1 values. For example, these are the images provided by Dr. Minting Wu from Kaohsiung BGH. For Fabry's disease, we have shorter T1 values in the myocardium. So we can have shorter acquisition time if we use MOLLI 8. Okay, so we use MOLLI 335 to collect MOLLI 8. Or we can use MOLLI 53. Right? We collect 5 images first and then collect 3 more images later. The scan time of MOLLI 35 or MOLLI 53 are the same. So we want MOLLI 35 or MOLLI 53. They look the same, but actually they are different. For MOLLI 53, it has longer T1 recovery. So actually MOLLI 53 allows longer T1 recovery. Then it can reduce heart rate variability and then improve T1 accuracy. Here we have some more major MOLLI variants. They are SH-MOLLI or Sasha. We don't have time to go over all of these. For the state-of-the-art T1 mapping, generally we use MOLLI 53 and the SH-MOLLI. The scan time is different. SH-MOLLI is faster, but it acquires less images. So actually, it's a trade-off between scan time and noise for the two sequences. Dr. Kelman had a summary about this. So for MOLLI 5.3 and SH-MOLLI, they perform very well. But about the T1 precision, the MOLLI 5.3 is better. Actually, we have more issues about balanced SSP readout, but we don't have time today. We have bending artifact, especially when we use 3 Tesla scanners. And we also have the phase problem of fat and water. If we use TR of 2 milliseconds in the 3 Tesla, the phases of fat and water are the same. So that is in phase for the left images. See? We can see the border of fat and water. If we use longer TR, for example, TR of 4 milliseconds, then the phases of fat and water are different. So they are out of phase. So we can see the border here. So using different TR values actually will affect the final T1 calculations. And we have some more issues about image registration. For the TI images, for the MOLLI images, the contrasts are different in all the MOLLI 11 images. So it is actually a difficult problem for image registration algorithms. So this is actually done by my student. We have some image registration algorithm for that. And we have some free breathing algorithm to acquire the T1 map. So you can see here we have free breathing acquisition and with some image registration. And then if we apply some image selection method, then we can get a nice T1 map with free breathing acquisition. These are the results of free breathing acquisition. For figure A, it is performed with breath-out. For figure 8, that's free breathing. So we can collect 10 slices of myocardium without breath-out. And then we also have some deep learning analysis for automatic HA segments. That's a work with Dr. Minting Wu. And then we also have an ongoing study which is called Hybrimoly. We combine the inversion recovery and the saturation recovery, and then we can collect more images with shorter time compared to MOLLI 5.3. And actually we can obtain similar image qualities of T1 maps with Hybrimoly with shorter time compared to MOLLI 5.3. Thanks for your attention.